Welcome. Today we are discussing on floating and sinking. At the end of the topic, we shall be able to see how a balloon is able to move up and move down. We shall also be able to see how a submarine is also able to sink in water and float in water, as well as other different bodies. So we want maybe to start with the key areas. So the first key area is the Archimedes principle, which states that when a body is partially or fully immersed in a fluid, it experiences an upthrust that is equal to the weight of the fluid displaced. That means that if you insert any object in a fluid, it can be, for example, water, it will displace certain amount of water whose weight, when measured, will be exactly as the weight of that object that you inserted or immersed in that fluid. Then the second law says that the law of flotation here, which states that a floating object displaces its own weight on the fluid on which it floats. This is supposed to be fluid on the fluid on which it floats. That means that also when you place any object on water, then it floats there to be able to displace a certain amount of water that is the same as its weight. So remember, it is floating by itself, not tied or supported by anything. So that is the key issue you are supposed to understand. So the nature of those objects, for example, in a liquid, we can start by this one. The object can be floating by itself on a liquid. So that means that it is partially floating or fully floating in the fluid without any support somewhere. So we say that the upthrust force, which is the upward force acting on that object in the fluid, will be the same as the weight of the object. That comes fully straight from these laws and principles. The second thing can be having an object, but now supported by a string at the base of the container, or if it's maybe in an ocean, at the base of the ocean. So we say that the tension in this string will be given by the upthrust, because if this string is cut, the object will be able to move upwards. That means the upthrust force is more than the weight of the object. So we now say that the tension in this string is the same as the upthrust force minus the weight of the object. Remember, we have said that when this string is cut, the object will move upwards, implying a higher upthrust force than the weight of the object. We can as well be having this diagram so that the body is supported, but not downward as this one, but now it's supported upwards with a string. Remember, when this string is cut, the object will fully be immersed in the fluid. So we say that the weight is more than the upthrust. Therefore, the tension in this string will be given as tension is equals to the weight of the object minus the upthrust acting on that object. Then the second sketch of the second diagram is for the application part of it. So you have an object here supported by another mass for the issue of turning effect. So we say that the apparent weight here, apparent weight is the same as the tension from this one. So the tension, which is given as the weight minus the upthrust, is the one acting here. So the apparent weight times this perpendicular distance is the same as this perpendicular distance times the weight of this object, so that you'll be able now to find the upthrust acting there from this issue of upthrust will be given as the weight minus the apparent weight. So remember, by the law of moment says that clockwise moment is equals to sum of anticlockwise moments. So we have here an application question that is supposed to be solved, so you can pause the video as well and write the question somewhere. A hot air balloon is tethered to the ground on a windless day as shown. So we have here a balloon that is tethered on the ground by this string. So they want you to determine if it contains 1,200 cubic meters of hot air of density 0.8 kilogram per cubic meter. The mass of the empty balloon is 400 kilogram. Density of the surrounding air, that is air surrounding the balloon, is 1.5 kilogram per cubic meter. So calculate the tension in the string holding the balloon to the ground. Remember, when this string is cut, the balloon will be able to move upwards. So how does that come? It comes from this thing. We have already said that this one means that the upthrust force is more than the weight of the object. So also here, the upthrust force is more than the weight of the balloon. So we now come and say that the tension in the string is given by the upthrust minus the weight of the balloon plus the air inside it. Then upthrust is given by the density of the air inside the balloon, which is also the same as the density of the air displaced, so times the volume, then times the gravity. So the density of the air inside of the surrounding air is 1.5. Density of the surrounding air is 1.5. Then the air inside it is 1,200. Then times 10. That gives us the upthrust as 18,000 newtons. Then the weight of the balloon plus its constituents or the ingredients in Z. So we have the mass of the balloon, that is 400 kilogram. Then plus the mass of the hot air inside. The mass of the hot air inside is given by the volume of the hot air inside times the density of that hot air inside. That is, mass is equals to density times volume. So you come up with the 400 times 10 to convert this one into Newton, then plus 200 cubic meters times the density of the air inside, then times gravity to get 13,600 Newton. So therefore, the tension will be given as the upthrust minus the weight. So it becomes 18,000 minus 13,600, leaving us with 4,400 newtons. It's supposed to be newtons as the tension in the string. That means this balloon can also support a weight that is equally 4,400 newton, and it won't be able to fall down. We also have another example here. You can also pause the video, then write the question somewhere, and even you can attempt it so that we proceed together. In an experiment to determine the density of a fluid, a uniform metal cylinder of cross-sectional area 6 square centimeters and length 4 centimeters was hung from a spring balance, then lowered gradually into a liquid as shown. So we have a spring here, then the body inside the fluid. So if the reading on the spring was 0.4 Newton, while the real weight of the solid was 1.2 Newton, so determine part 1, the volume of the metal cylinder. Remember, volume of the metal cylinder is the volume of this cylinder. We have the cross-sectional area as 6 centimeters square, then we have its length as 4 centimeters. So we know that volume is given by the cross-sectional area times the length. The cross-sectional area is this one, so we convert to SI unit. Length is this one, we could also convert the S to SI unit. So volume to SI unit divided by 1 million. Then, cross-sectional area divided by 100 squared, then this one divided by 100, giving us a volume of 2.4 times 10 raised to negative 5 cubic meters. The second question is the upthrust acting on the solid. Remember, upthrust acting on the solid is determined by the difference between this one. So from the diagram that you had already seen, which I can also still show you, we had already said that if it is suspended downwards here, the tension here, which is the apparent weight for that matter because of the spring, is given as the weight minus the upthrust. So similarly here, when this string is cut, it will be able to fall down, meaning the weight is more than the upthrust. Therefore, the tension, which is the apparent weight, is given by the real weight minus the upthrust. So making upthrust to be the subject, you get that upthrust now becomes the real weight minus the tension. The real weight is 1.2. The apparent weight or the tension is 0.4. So the difference gives us 0.8 Newton. Then the mass of the liquid displaced by the cylinder. The mass of the liquid displaced, remember we said from the law of flotation or the Archimedes principle that the mass or the floating object displaces its own weight, or the upthrust is the same as the weight of the liquid displaced. Therefore, the upthrust, which is 0.8, is equals to the weight of the liquid displaced. So it becomes the upthrust, which is 0.8 from here, is equals to the mass times gravity. So making mass to the subject leaves you with 0.08 kilogram. So the last part is density of the liquid. Density of the liquid, you have mass, then you have the volume here. Density is given from this mass and this volume. Density is given by mass over volume. So take this mass, then divide by this volume to get this one as density of the liquid. Among other areas of application, we said we have the submarines. So it's applied in submarines. The issue of balloons, which we have already seen. We also have another application here of the hydrometer. So for hydrometer, you have these parts. So you're supposed to label this one as the stem. We have a scale here. We have a bulb. We We have this bottom with some lead shots or some sand just to add weight. So you have their function here, that the stem is normally narrow for higher accuracy or sensitivity. Then the bulb is wide, so you can see it's very wide, so that it can displace more fluid for it to float. Remember, an increase in volume will increase the upthrust force, enabling it to float. Then you also have the lead shots that has some weight, so they are adding weight so that it can stand upright or vertically in the liquid. Then we say that the higher density appears at the lower part, and the lower density appears at the higher part, so that this one can be a more denser liquid, then this one will be a less denser liquid. For example, if you have a 1.2 grams per cubic centimeter being compared to 0.8, so 0.8 is less denser, comes at Q. 1.2 is more denser, comes at 1.2. So kindly, if you have any question pertaining floating and sinking, drop it on our email at the bio. Then kindly, subscription is normally free for support. Thank you.